Now let's answer the question everyone asks. How does AI ops actually work? Is it simply ChatGPT reading log files? Not at all. In fact, most AI ops platforms rely much more on traditional machine learning than on large language models. Think of AI ops as an experienced operations engineer who's been working in your company for the last 10 years. That engineer knows things like the payroll application always spikes every Friday afternoon. Backups always create extra network traffic around midnight. Every time we deploy version 5.2, storage latency increases for about 10 minutes. Humans learn these patterns through experience. AI ops learns exactly the same way. But instead of watching hundreds of systems, it watches millions of events. Every second, every day, every month, without getting tired, without forgetting, without taking vacations. The first thing AI ops does is observe. It doesn't immediately make decisions, it simply watches, weeks, sometimes months. It learns what normal looks like for every application, every server, every service, and every business hour. Because here's something traditional monitoring never understood: normal changes. CPU usage that's perfectly healthy at 2 p.m. on Monday might indicate a serious problem at 2 a.m. on Sunday. Static thresholds don't understand context. Machine learning does. Let's look at one of the simplest and most powerful capabilities: dynamic baselines. Imagine you're managing an online retail platform. Every year during Black Friday, CPU usage reaches 95%. Traditional monitoring says 95% CPU. That's critical. So your engineers receive hundreds of alerts, but nothing is actually broken. The system is behaving exactly as expected. Now imagine it's 2 o'clock on a quiet Sunday morning. CPU suddenly jumps from 15% to 60%. Traditional monitoring ignores it. After all, the threshold is 90%. But AI ops notices something unusual. It knows this application has never behaved this way at this time. It raises an alert, not because the number is high, because the behavior is abnormal. That's an enormous difference. Instead of monitoring numbers, AI ops monitors behavior. This dramatically reduces false positives. Your engineers stop chasing harmless events and start focusing on genuine problems. Now let's look at the feature that saves operations teams the most time: alert correlation. Imagine one network switch inside your data center unexpectedly fails. Within milliseconds, 50 servers lose connectivity. Applications become unreachable. Databases disconnect. Monitoring agents stop reporting. Storage systems raise alarms. Your monitoring platform doesn't understand relationships. It simply reports what each system is experiencing. So instead of one problem, your NOC suddenly receives 200 separate alerts. Every alert looks critical. Every alert demands immediate attention. Chaos begins. Engineers start opening duplicate tickets. Different teams investigate different symptoms. Everyone works incredibly hard on exactly the wrong problem. AI ops approaches this completely differently. Instead of treating every alert independently, it asks three questions. Did these alerts happen at nearly the same time? Do these systems depend on one another? Have we seen this pattern before? Within seconds, the AI realizes all 200 alerts share a common dependency: one failed switch. Instead of generating 200 tickets, it creates one, titled core switch failure affecting 50 downstream systems. That's what your engineers investigate. The symptom disappears. The root cause becomes obvious. Mean time to resolution drops dramatically, not because engineers became smarter, because they stopped wasting time. One of the least understood yet most valuable capabilities inside AI ops is topology mapping. Every modern application depends on dozens, sometimes hundreds, of other services. Imagine you're opening your banking app. Seems simple. But behind the scenes, your login request travels through a load balancer, an API gateway, identity services, authentication servers, fraud detection, customer profile services, account databases, notification systems, logging platforms, monitoring agents, cloud networking, storage arrays, DNS, and firewalls. If just one component becomes unhealthy, everything downstream may appear broken. AI Ops continuously builds these dependency maps. It understands which systems rely on others. That means when something fails, it can distinguish between the actual cause and everything merely affected by it. That's incredibly difficult for humans, especially in environments with thousands of services. Finding the root cause of an incident often takes longer than fixing it. Why? Because humans naturally investigate symptoms first. AI Ops works backwards. It asks, what changed? Maybe a deployment finished 3 minutes before the outage. Maybe someone modified a firewall rule. Maybe a cloud auto-scaling policy failed. Maybe a storage array reached capacity. Maybe a certificate expired. Maybe a DNS record changed. Instead of asking engineers to search across 5 different systems, AI Ops automatically gathers context. It checks recent deployments, infrastructure changes, change requests, cloud events, configuration changes, and historical incidents. Then it presents engineers with something far more valuable than raw alerts. A hypothesis. For example, probability 93%. Root cause likely introduced by deployment version 5.4 on Kubernetes cluster East. Similar incident occurred 47 days ago. Resolution, roll back the deployment. Estimated recovery time 6 minutes. Notice something important. The AI isn't making random guesses. It's learning from history exactly like experienced engineers do. Only much faster. Let's make this real. Imagine a telecom operator. Customers suddenly report dropped voice calls. Traditional monitoring generates alerts from session border controllers, SIP trunks, DNS, media gateways, firewalls, and routers. Hundreds of alarms. AI Ops correlates everything. It discovers all affected calls pass through the same session border controller. The actual problem: one software process consuming excessive memory after a recent patch. Instead of investigating dozens of network devices, engineers immediately restart one affected process. Service restored, minutes instead of hours. Now consider a bank. A payment gateway suddenly becomes slow. Customers think payments are failing. Developers investigate application code. Database administrators inspect SQL. Network engineers check latency. AI Ops notices something everyone overlooked. A storage array firmware update completed 8 minutes earlier. Every affected database shares that storage. Problem identified. Rollback initiated. Millions of dollars in failed transactions avoided. Or take a cloud platform. A Kubernetes cluster begins scaling unexpectedly. Traditional monitoring reports CPU issues, memory issues, container restarts, and pod failures. AI Ops identifies the real trigger. A single misconfigured auto-scaling policy, one configuration change, hundreds of symptoms, one root cause. So far, we've answered 2 important questions. What is AI Ops, and how does it actually work? But if you're an IT manager, you're probably asking something completely different. How do I convince my CIO to invest in this? What's the return on investment? Which vendor should you consider? Why do so many AI Ops projects fail? And perhaps the biggest question of all, will AI eventually replace NOC engineers? Let's answer those questions in Part 3, where we'll explore the business case, implementation strategy, common pitfalls, and the future of autonomous IT operations. For informative videos like this, Like, subscribe, and hit the bell icon. See you in the next video.